Alrighty, good day, folks. We'll be getting started with the webinar here in a couple minutes. Couple housekeeping items before we jump into today's session. The session will be recorded and available for playback at the end of the webinar time today. So if you have to jump off for any reason, or if you have some colleagues that you think might find this information interesting, you can catch up on or share this link at the end of today's webinar. I'll also make note of the Q&A feature. So for those that want to stick around towards the end, once the session is complete, we will be doing a live Q&A. So in the bottom right, there's a specific option to submit any questions. So if there's anything related to the content that's presented, maybe something related to the work that you're doing. If you have any questions or want to shoot those through, please feel free to do so, and we'll reserve some time at the end to go over those together. All right. So yeah, about a minute past here, we'll go ahead and get started. Let me do adjust. There we go. So thank you all for joining today's webinar. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. Kind of introducing us today to our session on thermomechanical analysis, or TMA 101, Theory and Applications. I'll be joined here shortly by my colleague, Alex Mann, who is a materials testing engineer here at C-Therm and the Thermal Analysis Labs group. And he's going to be really going through the bulk of today's content. I'm just going to start out with a quick little introduction for those that are maybe new to these events, new to C-Therm, a little bit of background on who we are and what we do. So at C-Therm, we primarily focus on thermal conductivity. Really, we are leading in the transient class of measurement technique. Really, our purpose and goal here is really to simplify thermal conductivity testing for the materials of tomorrow. Now, we do this through advancements of transient-based methods, primarily on our flagship product, Trident. Trident brings together multiple methods for thermal conductivity testing. This is one instrument which provides a really nice avenue to establish testing capabilities on a variety of material formats, testing conditions, etc. So while it won't be the focus of today's session, of course, if you did have any interest or wanted to learn more about thermal conductivity characterization, please feel free to reach out. We are also partnered with both Rigaku and Metrovib North America for their line of thermal analysis and mechanical analysis testing instrumentation. Of course, today we will specifically be going over Rigaku's TMA product line, and that'll be the main focus. I will also make note of Thermal Analysis Labs. That is our contract testing division. TAL offers all of the thermal analysis testing that we have from our CapEx side, as well as other relevant methods that exist in industry. So whether you're looking for instrumentation or testing services, again, please feel free to reach out. These are all things we're happy to support with. So, throughout these different methods and different tools that exist, really, one of the quotes that we like to reference here is this one by Abraham Maslow: when all you have is a hammer, everything looks like a nail. Often this is something that we see, especially on the thermal conductivity side. So where you take a good method of measurement, but apply it to a material or a testing condition just wasn't designed for. So again, being able to take access to the best option at the time, whether that's taking the modular approach, such as what the Trident platform offers, or looking at some specific thermal analysis tools. Really, we're here to help support those endeavors. And again, if you have any questions in terms of what might be the best route to go forward for your specific application or testing interest, we're happy to support those endeavors. So I'll just make a note. I did see someone with their hand raised, so we won't be going over any kind of live questions throughout the session, but if you do have any questions, again, please feel free to type those into the Q&A box, and we'll get to those at the end of the session. For those that are interested in thermal conductivity, I will just make reference to our method selection guide. This is a free resource available on our website for download. If you're any questions or maybe you're getting into thermal conductivity or just want to learn a little bit more, this is a great free resource which goes over all the methods that are available on Trident plus others that are available in industry. So it's a great starting place to get yourself into the different options that exist out there for testing. And lastly, here, before I hand it over to Alex, we always like to end with a client testimonial. These are the folks that are using our instrumentation or who have worked with us. Wanted to share this one here today from Heidi, who's an R&D manager at Peterson Chemical Technologies Limited, noting that what we appreciate the most was how very knowledgeable and helpful the people at C-Therm have been throughout the setup and learning process. They have designed this high quality, powerful, and complex instrument so that it is easy to use and incorporate into our thermal testing capabilities. So, if you're interested in what other folks are saying, we do have a testimonials page available on our website. Definitely feel free to check that out to see what folks have to say about their experiences with us. And lastly, yes, we actually are offering a Rigaku academic support program. So for those that are on the line from different, academic institutions, universities, if you are looking to bring some testing capabilities in-house, there is currently a nice program going on right now. You can kind of see the options listed on screen there. If you were about to potentially, again, investigate some different instrumentations to accommodate thermal analysis testing, so that's DSC, STA, or TMA, which we'll be focusing on here today, definitely feel free to make note of that. There's quite a nice program running currently. All right, with that being said, that kind of brings me to the end of kind of the introduction here. It's now my pleasure to introduce Alex, who will be taking us through the bulk of today's session. So I'm going to stop sharing here, Alex. Feel free to take over.
Wonderful. Thanks, Arya. I'm just going to get set up real quick, and then we should be good to go. All right. As I already mentioned, my name is Alex, and I work kind of in the lab at C-Therm as well as subject matter expert with the Rigaku products. So C-Therm is the North American distributor for the Rigaku line, which includes their thermal analysis lineup of differential scanning calorimetry, DSC, our simultaneous thermal analysis, our DSC TGA, as well as what we'll be focusing on today is the TMA. Now, all these methods are, semi-related and really pair well together, but unfortunately today we're just going to go over the TMA. So first off, most basic, what is TMA? It stands for Thermomechanical Analysis. It quantitatively measures the change in the length in response to temperature. Sorry about that. I've been told that I did something wrong. I'm going to share my screen again. Sorry, guys. There. I think that should be better. Yeah, so I guess moving off where I picked up. Uh, oh, sorry. All right, hopefully now we can get going. So again, as I mentioned, TMA, thermomechanical analysis, really measure the change of length in response to temperature. So it really measures how much a sample will grow or shrink when heated or cooled, whether it's steady through that temperature range or whether it goes through a thermal event. It can measure it. So then moving on to the basic principles, as we can see here, we have our TMA, and we have our furnace, and then we have some of the measuring instrumentation up here on top. So if we were to kind of use our X-ray vision and look through this, we would see that there is a sample, which just sits on the support tube, and then the detection rod goes up into the electronics. So essentially the way it works is that whenever the sample expands, it will push up on the detection rod, which will then measure it. So as we can see here, this is our support tube, is what the sample rests on. And here we have our sample, and then the detection rod, which gets pushed up as the sample expands. So I'm going to introduce two kind of different styles of TMA or theory. First is going to be the standard TMA. So as we can see here, our observed is kind of the data that is recorded by the instrument, and it's going to be equal to what the core sees. So the core is going to see the expansion of the sample, but also it doesn't really know where the expansion is coming from. It just measures expansion. So in reality, it's also going to see the expansion of the detection rod as well as the support pipe. So that's what we get when we do a single rod TMA. Now, for this reason, our support pipes are made of materials that have a very low CTE. So that way, we are able to rarely negate this error if our sample's thermal expansion is really large. So as you can see here, we tend to use quartz because it has a very low thermal expansion. As we get to higher temperatures, it's made out of alumina, which then gets to around the CTE. So for our differential TMA, now we have two rods. So as we can see here, not only do we have a sample, but we also have a reference material that we're measuring simultaneously. So the way this one works is that the reference pushes up on the detection rod and it moves the coil. Now the core is attached to the coil. So what that means is that the observed or the data that we're going to get is going to be the core minus the coil. Now, because both the reference and the sample both see the detection from the expansion of the detection rod and support tube, they're going to cancel out because it's subtraction. So this gets us with the data that we see is going to be the sample minus the reference. Or we can, move that around, rearrange it to be that the sample is going to be the observed minus the reference. And because it's the reference value that we pick, we're going to choose a sample that has a very known and well-documented expansion. And this way, if your sample has a very, very low thermal expansion, you can still get really accurate and precise results. So this is kind of what the two different differential and standard look like. We can see here the standard, we just have one rod. And then in the differential, we have two rods, one rests on the sample, which is right beside the reference, which has its own rod. So once you put your sample in and you run it, this is going to be the data that you get. On the y-axis, normally you will have either change in length in microns, the expansion as a percent, or the total length. So if this was 10 centimeters, you could see this expanded by 40 microns. So normally the expansion is a straight line, but as you can see here, we have a lot going on in this graph. So this is a polymer. So this is the glassy region. Then eventually it's going to transition to the rubbery region. And we can notice that the expansion is linear in both regions. However, the rate of expansion changes when it goes through the glass transition point, which we determine by using the tangential method. So we're going to take the tangent of this line and the tangent of this line, and we're going to continue it, and the point where they intersect is going to be our glass transition point. Now we notice up here, this is the dialectrometric softening point. So when you have something like a polymer or a glass, eventually when you heat it up, it's going to start to have some viscosity and it's not going to be able to hold its form. So as it gets soft, eventually the rod will begin to push into the sample instead of the sample pushing on the rod. So we get this softening point, which is pretty good for determining, comparing the softness of different samples. So we're going to talk a lot about CTE, or the coefficient of thermal expansion. So just to make sure we're on the same page, I'd like to describe it. So it's just a really number that is used to describe how much a sample is going to expand or shrink with temperature. Units of this include micron per meter Celsius, parts per million per degree Celsius, or 10 to the negative 6 per degree Celsius. Now, all of these units are the exact same, just worded a little bit different. I prefer to use ppm per degree Celsius because I find the rest tend to be a mouthful. So when you're measuring the CTE, we're measuring the change in length. So we need a starting point because we need what point are we changing from? So every CTE measurement should include what the reference temperature was. So we have this here as our L naught, the little zero, which describes our initial value. Most often or not, it's a room temperature, but sometimes people want it different values, so you can really change it to whatever you'd like for your application. So the formula, pretty straightforward. It's 1 over the initial length times the change in length divided by the change in temperature. Or we can expand that out to say, the change in length over the initial length. This is also equal to the percentage, and then divide or times the change in temperature. So for some expected CTE values, of course, there's always exceptions, and this shouldn't be, this should be taken with a grain of salt. But generally, most often, glasses will have the lowest thermal expansion, often between 0.5 and 10 ppm per degree Celsius. After that, we move on to ceramics, which will expand a little bit more, normally between 5 to 15. Then we have metals, which can go from 10 to 30. And lastly, polymers tend to have the highest expansion out of all the material types. So the importance of CTE. Firstly, it's always good to know how your material behaves at different temperatures. Some applications require materials to have a constant performance over a wide range of temperatures. It also allows us to determine the density as a function of temperature, which density is very important in many models, formulas, etc. Also, thermal expansion can lead to unwanted stress or even failure in scenarios. And it also determines compatibility and the limits for material pairings, such as a composite, stacks, substrates. As we see here in the bottom, we've got a nice little graph which can show warping and or delamination when you have two different materials that are heated up or cooled. So brittle material, especially glass and ceramics, are very susceptible to thermal shock. So essentially, when it is rapidly heated or cooled, or even if there's a localized area of heating, it can cause the material to break. So lowering the CTE of the materials will actually help increase the resistance because they will, shrink and expand less due to these uneven heatings or, quick heatings. One example of this is cooking. Pyrex is very commonly used as a glass or a ceramic. It has a low CTE of 3, so that way, whenever you take it out of the oven and you put it in the room temperature to cool, it doesn't shatter, it doesn't break. Or if it's still warm and you were to put it in the sink to clean, that thermal shock won't cause it to break. Additionally, there's also warping that needs to be considered. So if material's expansion, it's restricted, or if it's cooled too fast or unevenly, it can cause warping. Really susceptible for polymers, metals, woods. So one example here is if you're connecting two dissimilar metals, then they're exposed to a temperature change. How are they going to react? Are they going to stay, connected, or are they going to warp and cause stress or failure? That's kind of why thermal expansion is important. Now, lastly, what if we combine a brittle material and a ductile one? A great example is glass to metal seals. So these are airtight seals. They're used for electronics, vacuum tubes, light bulbs, diodes, reed switches. For the seals to work, the CT of the glass and the metal have to be similar. So in order to create these, the glass is heated up and molten, and then the metal is inserted. So when the glass cools down, if the metal is going to shrink more than the glass, it can cause a tensile force in which it'll shatter. So for this to work, we really need to make sure that the metal and the glass have a very similar CTE. So we're going to move on to some Rigaku TMA, learn a little bit about this instrument here. So this one has the option of doing standard or differential TMA. So you can either use one rod or two rods. There's multiple furnace options which can be switched by the user. So we have the low temperature furnace that can go down to -150 all the way up to 600. There's a standard furnace which goes up to room temperature up to 1100 degrees Celsius. Now, if you need to go past 1100 degrees Celsius, this is the point where you need to switch from quartz up to alumina, because past this, the quartz will start to get soft. That's its end working temperature. And lastly, there is a high temperature furnace that can go all the way up to 1500 degrees Celsius. Past 1100, again, you have to use alumina. There's also different attachments, such as the thin film attachments, if you want to measure the expansion or contraction of thin films. There's a 3-point bending, a penetration or softening, and lastly, a humidity generator, among others. So for the detection rod, there's really two types that Rigaku offers. There is the point contact and the surface contact. So the point contact takes the force and concentrates it into a point, giving high pressure. This is really good for contact against the sample and the rod. It's really ideal for materials that won't soften. So metals, ceramics, etc., where the sample isn't going to deform by this high pressure. Then there's the flat type where it evenly distributes the load over the top of the sample. This is great for polymers, glasses, where once they get soft, the force could cause the styliometric softening point that we spoke of earlier. So for the TMA, the ideal sample size is between around 10 to 20 millimeters. So essentially, the larger sample size gives a better resolution. So, if the sample is larger, the expansion is, a percentage, so it's going to be larger. And it's way easier to detect larger expansions than it is smaller expansions. That's why 10 to 20, 20 being, the ideal. And then for the diameter, this really boils down to, a larger diameter will cause an uneven temperature distribution or will cause the chance of an uneven temperature distribution. And lastly, smaller samples, you can go less than 5 millimeters diameter, but they tend to become unstable around there. So additionally, the ideal sample actually has kind of a hole burrowed into the bottom of it. So for things like STA, DSC, and TGA, they use really small sample amounts, around 5, 10, 15 milligrams, which means that the temperature uniformity of these samples is always pretty good, very close to what the furnace temperature is. However, for the TMA, we have these large samples which weigh on the gram scale instead. So because we have so much more mass, we can get thermal inertia, which causes the thermocouple to lag behind the actual temperature. So due to this hole burrowed in the bottom, Rigaku's thermocouple can be placed inside the sample. So that way, the temperature that's recorded is the internal temperature of the sample. So as we can see here, our reference sample has a little hollow cavity, which the thermocouple can be inserted inside. And also, this sample here, our reference nickel sample, also has a little hollow cavity, so you can put the thermocouple inside the nickel. Now, if your sample can't have this little hole in the bottom, well, then in that case, you would just use the reference to more closely mimic what the sample would see. So here are the thermocouple locations. So on our left side, we can put it inside the reference. We can put it out in the open if you are more interested in the furnace temperature than the actual temperature of the sample. And then as well here, we can put it inside the sample. So we have the left in the reference, middle out in the open, and then right inside the sample. I'd also like to highlight real quick a anti-fusion discs or spacers. I've talked a lot about softening and with polymers and glass. And when it gets soft, sometimes it sticks. So we don't want the softening sample to damage either the holder or the detection rod. So what Rigaku has are these little spacers here, which are sacrificial. You place them on the top and the bottom. So that way, if there is any melting or fusion occurring, the sample will just stick to the to the spacers, and the detection rod and the support tube will be clean and ready to use, no damage. Going back to temperature for a sec, we can actually combine these spacers with a standard reference metal, indium, tin, lead, aluminum, and we can use this to actually, calibrate the thermocouple. So as we can see, these all have sharp melting points. So we can see this sharp melting point, use our tangential method to determine the melting temperature. And then from that, we can even more increase the accuracy of the thermocouple. So I mentioned that 10 to 20 millimeters is the ideal sample, but what if I can't make a sample that size? Well, that's fine because Rigaku also has the differential stage TMA, great for samples that are less than 10 millimeters. So essentially, we take another reference piece, in this case, quartz, we use it as a stage, and we set our sample on top. And the software uh, takes all these as an input, and it gives you the correct thermal conductivity by canceling out the stage and just accounting for the sample. This is great for samples that are, small, such as pellets, sheets, pills, wires. What if your sample cannot be shaped or it's really hard to work with and we just have a small amount? And lastly, if it undergoes significant thermal expansion from an event, we might want to have a smaller sample. So, I always said that a bigger sample gives increased resolution, it's better. So how does having a smaller sample affect the result with this differential stage method? So here, this was done using a copper plate. It was around 0.4 millimeters tall or thick. And, at around 300, we measured a 2.71% error, which is pretty good considering its unideal situation. And also, it's worth mentioning that copper, 17 isn't the most largest expansion. This method really works well with polymers. It can get really high accuracy with polymers because they expand so much. So quickly, I'm going to go over some applications of the TMA, all done using Rigaku. So firstly, I'd like to introduce Invar. It is a nickel iron superalloy. It comes from the name invariable because the properties don't change with temperature. It's very stable. And depending on the actual ratio of iron to nickel, the CTE can vary from 0.5 to 20 parts per million. So this just goes to show that if you have an alloy, well, then you can't really guesstimate or predict the CTE just based on the composition. You really need to measure it. And this also relates to heavily doping an item, maybe in the semiconductor industry. So you can't just assume that the CTE isn't going to change much or that it's going to be an average of the two. You really need to measure your material. While speaking about Invar, here we have the comparison of two nickel alloys, so stainless steel and Invar. They're both nickel iron alloys, comparable strength, same density, same hardness. But as you can see here, the stainless steel expands around 16 times more than the Invar, which has a CT of 1. And every source states that Invar has a CTE. It only goes from 200 to 100, sorry, 25 to 100. And I kind of always wondered why past that was omitted. So this test actually expanded to 300. And as you can see, stainless steel's expansion remains linear over this range. However, Invar loses its famous low expansion properties, probably at around 150-ish. And now the expansion is only about a quarter compared to what it was a 16th before. So moving on to another example is a solid-solid phase change or transition. So nitinol, again, is another nickel alloy, nickel titanium. It has two main phases, which is the martensite and the austenite. This makes it useful in actuators, medical stints, sensors, non-pneumatic tires. As we can see here, as it goes through its phase transition from its martenite to its austenite, it shrinks quite a bit. Now, for a metal alloy, this might not seem like that big of a deal, but for ceramics, which are very, very brittle, this sudden contraction or expansion can cause it to shatter. So this also relates to doping, where you add a different compound in order to, shift these shift the phases. Next, we're going to look at the expansion of a PCB. So inside the blue, as you can see here, we have an old PCB, which was exposed to dust, moisture, vibrations, bending, heating and cooling over around 10 years. So as a result, we can see that the glass transition actually shifted by 10 degrees Celsius, and the expansion is much greater than it was before. So this just goes to show that, yeah, the TMA can measure expansion, but also the test is what you make of it. So you can easily do, an aging study such as this to compare how your material will be in the future. Next, I'm just going to introduce some ceramic sintering real quick. So as we can see here, we have our pellet. It rests above and below these spacers or these discs in order to prevent our detection rod. And the pellet has been pressed using a binder and the ceramic particles. So as the binder burns off and the temperature increases, the particles become sticky and they'll stick together. Very important for ceramics and even metals for such as 3D printing. So as we can see, we get the sintering temperature around 773 Celsius, and then we actually get the total shrinkage of around 20%. So this is really good for predicting the, you know, sintering profile, what temperature it occurs at, and as well as the density. Because, as it shrinks, it densifies. So real quick, we're going to take a look at an example from literature that was done using the Rigaku TMA, the monolithic oxide metal composite thermoelectric generators for energy harvesting. So what they did was they have a thermoelectric generator, which is a bunch of layers stacked on top of each other. And these were green body ceramics, meaning that they were not fired. So we had the P-type, which was a lanthanum strontianide titanate. We had our N-type, which is nickel molybdenum, and then our insulator was zirconia or yttrium doped zirconia, and they were stacked on top of each other in these layers. So the reason that they wanted to measure the shrinkage during sintering is because these are meant to be co-fired, which means that they will all be fired pre-stacked at the same time. So if the CTEs are different, then it can cause stress, fracture, etc. So the results were that using these materials, they determined that the sintering profiles were very similar. They had a shrinkage rate around 15%. So therefore, these materials were good to be co-fired and sintered together as one. So next, I'm going to do a quick application on the humidity generator. So one thing I'd like to notice is, or point out, is that you see kind of two temperatures profile, or not profiles, but ranges. This is just because the humidity generator, it takes in the room temperature dry nitrogen. It can heat it up anywhere between room temperature to 85 and give a humidity anywhere between 5 to 90% relative humidity. And then that goes through the insulated tube into the TMA, which then that can go up to room temperature 1500. So this means that studies can be done, with the fabric or a plastic measuring the expansion at around room temperature to 100, room temperature 200, but also it can be used for sintering studies in wet environments, which will, as we'll see, will greatly affect the conditions. So this was the multi-layer ceramic capacitors expansion compared to a dry and a wet atmosphere. So these are produced by alternating layers of metal and ceramic. So we have a ceramic sheet. On top of that will be a metal. And here at the bottom, we have another ceramic sheet. On top of that will be a metal. This is where we get our sandwich. So we had the binder and the barium titanate ceramic. Sample thickness was around 1 millimeter, up to 1300 from room temperature, 5 minutes, done in a dry and wet atmosphere. So as we can see here, whenever the sintering was done in a wet environment, the sintering began much sooner, and as well, it sintered much more by around 21, 22% compared to probably 16, 17% in the dry environment. So what this means is that for this compound, if you want your material to be denser, harder, stronger, more thermally conductive, among other properties, well, then it should be sintered in a wet environment. Next, I'm going to look at different attachments, thin film expansion. This is really good for use with thin films, sheets, fibers that are 10 to 200 microns long. So normally, TMA is measured in compression with the rod sitting on top and small force down. Over this one, the detection rod pulls up. So we set the thin film sample in clamps. We pull up in tension with this, and this metal boot here is used to secure it against the bottom of the holder. So this does have a thin film mounting jig. So what this is done or used for is to ensure that the sample is flush and that it's the correct length. So as you can see here in the sample, there are the mounting brackets that slot into here, and then it is screwed on. This is just a quick video that shows how it's loaded, again, using the metal foot against the bottom of the support tube, and then this detection rod for tensile pulling up on the sample. So our sample, which has already been clamped, is put inside. Next, the detection rod pulls up, causing the tensile force. And then the metal boot is put underneath to hold it in case there's any shrinkage or to stop the sample from moving. And there's not much else to it. So here's a test that I did to determine how a copper thin film handles temperatures over extended period of time. So essentially what we have here is our temperature profile was a ramp up to around 100, hold for an hour, ramp up to 200, hold for an hour, etc. So what we saw was that at around 100, there was really no expansion during this isotherm. You're not increasing the temperature, you're not seeing expansion. That's what we want, that's what we expect. Up around 300, even though we weren't increasing the temperature, we started to see that there was some expansion. Then up to 400, we saw that even though we weren't raising the temperature, we're seeing a lot of expansion, and then the same as we go up here. So essentially what was happening is the copper was, oxidizing, and as we held it longer in the furnace, and then right here we can see on the cool down, it didn't return to normal because it had taken, irreversible damage from the oxidation. This is the same test. I just rearranged the data into a thermal hysteresis curve. So as we can see here, we're expanding, it's nice and linear. At around 100, the isotherm didn't really damage it that much. At around 200, we see a little bit, but not really that much damage. Around 300 is where we start to see this damage occur. 400, we see a lot of expansion, and at 500, a lot more expansion. And then this damage done is irreversible. So on the cooling down cycle, we have around 140 microns of permanent deformation. And I'd like to thank you folks for coming out and, bearing with me during the quick technical difficulty during the beginning. And I'm going to pass it back to Arya, who's going to say a couple closing words before we get into our questions.
Alrighty. Thank you very much, Alex. Yeah, folks, so just bear with me for a sec. I'm going to go into a little bit of an outro here, a couple closing remarks, and I have seen some questions come in through the Q&A. So again, if you do have anything that you want to talk about or any questions, please feel free to type those in for us. But that being said, just get this up on screen here. All right. So, if this type of content was interesting to you, or if you kind of want to learn a little bit more about some of the other areas of application, we do have a slew of technical resources and past webinars available on our website. Please feel free to check those out. You'll also be able to check out any coming webinars and other content pieces that are going to be released in the coming weeks and months. Speaking of those in particular, I will just flag a couple ones that are coming up. These are both going to be focusing primarily on thermal conductivity, but we have one on September 16th, more of an application-focused webinar investigating thermal properties, thermal conductivity of aerogels and low-K insulative sample behavior. And then later in the month, towards the end of September, we'll be doing a thermal conductivity of polymer composites webinar. So a little bit more broader application focus on those two. I will also flag a couple upcoming in-person events. If you happen to be in the area, you're planning to go to one of these, we're more than happy to kind of schedule a one-on-one or, kind of stopping by our booth. Happy to have a chat. We're going to be at JASIS, which is held in Japan. This is September 3rd to 5th. We will also be at the Global Polymer Summit in Cleveland, Ohio, in the US, September 8th to 11th. And then finally in October, the Battery Show North America, which is again in the US in Detroit, Michigan. So, if you would like to learn a little bit more, maybe do more of a one-on-one discussion about specifically your application as it relates to any of these different testing capabilities, we always offer the ability to do a free technical consultation. Gives us, again, more of a time to focus specifically on your given application and materials. So if this is something that would be of interest, again, these are free to schedule. Definitely feel free to take advantage of that. If what you've seen is maybe spark some interest and you're looking for some budgetary information, whether that's for any of the thermal conductivity instrumentation, the Rigaku systems, etc., please feel free to reach out. We can provide free quotes to help establish some of those costs and kind of going into the budgeting time for you. So again, these are completely free, so definitely take advantage of those. Now, if you're looking to maybe go into some of these testing capabilities, but you're not looking to bring anything in-house, again, our thermal analysis team does offer, as you can see, all of the different methods that we have through instrument purchase. We can also provide testing solutions as well. Everything from the thermal conductivity to expansion, etc. A variety of ASTM and ISO compliant testing methods are available. Please feel free to check those out. Lastly, I'll kind of put an ask out there. If you're not already doing so, give us a follow on LinkedIn. This is really where we post all of the latest and greatest content, upcoming webinars, blog posts, content pieces, etc. So if you're not already doing so, give us a follow on there to keep up with what we're doing. And with that, yes, I believe that brings us to the end. So we're about to go into the Q&A section here, but for those that need to drop off at this point, just for myself and reiterating what Alex had said, thank you for joining us here today. Hopefully you found this content insightful. And again, for those that are interested in staying on the line, bear with us for a couple minutes and then we'll jump right into the Q&A session.